Suppose a doctor finds a tumor. How can a machine decide whether it's benign or malignant? Could we simply draw a straight line through the data and hope for the best? It turns out that approach fails surprisingly often. And solving that problem led to one of the most important algorithms in machine learning. The story begins with a problem. Imagine trying to predict house prices. Sometimes a straight line works, but real-world data often bends and curves in ways a single line can't capture. One solution is to create new features. Maybe use x squared, or the square root of x. But how do you know which features are best? Researchers found another approach. Instead of fitting one model to the entire dataset, what if we focused only on nearby examples? This idea became locally weighted regression. When making a prediction, the algorithm pays the most attention to training examples that are close to the point of interest. Nearby examples get more weight. Distant examples get less weight. As a result, the model can naturally follow complex curves without manually designing new features. This also introduces an important distinction in machine learning. Linear regression is a parametric algorithm. Once it learns a small set of parameters, it can forget the training data. Locally weighted regression is different. It must keep the training data around because every new prediction depends on nearby examples. That makes it a non-parametric algorithm. But another challenge soon appears. What if the goal isn't to predict a number? What if we want to predict a category? For example, is a tumor benign or malignant? At first, it might seem natural to use linear regression. Draw a line. Then classify everything above a threshold as one class and everything below as another. But there's a problem. A single new data point can dramatically change the line and produce very different classifications. Linear regression simply isn't designed for classification. Researchers needed something better. That solution became logistic regression. The key idea is surprisingly simple. Instead of predicting any number, logistic regression predicts a probability, a value between 0 and 1. To make this possible, it uses a special function called the Sigmoid Function. No matter what value goes in, the output always stays between 0 and 1. Now the model can answer questions like, what's the probability this tumor is cancerous? Or what's the probability this email is spam? But building the model is only half the challenge. How do we find the best parameters? Just like linear regression, researchers use optimization. But instead of minimizing squared error, logistic regression maximizes something called likelihood. In simple terms, the model tries to find parameters that make the observed data as likely as possible. One approach is gradient ascent. It repeatedly updates the parameters, moving toward better solutions step by step. But researchers also developed a faster alternative, Newton's method. Instead of taking many small steps, Newton's method uses information about the shape of the curve to make much larger jumps toward the optimum. In many cases, it reaches a good solution in far fewer iterations. And that's the journey. When straight lines aren't flexible enough, locally weighted regression allows models to focus on nearby examples. When prediction becomes classification, logistic regression transforms outputs into probabilities. And optimization techniques like gradient ascent and Newton's method help these models learn from data. But there's an even bigger question. Can we build an entire family of machine learning algorithms from the same set of principles? And what happens if we design a learning algorithm that makes decisions more like a neuron in the human brain? Those ideas led to two of the most influential concepts in machine learning, perceptrons and generalized linear models. And that's exactly what we'll explore in the next video.